Hi, welcome to ESI 412, Nanotechnology, Materials, Infrastructure, and Safety. I'm Professor Ukjun Nam at the Pennsylvania State University. So this is the lecture outline. So we're gonna talk about the overview of the focused ion beam, and I'm gonna talk about a little bit about the operation and then the application of this technique. So we talked about this ion beam and then electron beam at the lectures for the electron beam lithography. And then as we discussed, this ion beam has a much smaller interaction volume compared to the electron beam. As to the signal, it just produces similar signals, and then the ion beam, in addition to this signal, depends on the energy of the ions. It can just sputter out ions. So that's the biggest differences. So these are four major applications we can use this focused ion beam. And then we already talked about this ion beam lithography. And then since those kind of interaction volume with the substrate is kind of pretty small compared to the electron beam lithography, so that is why this ion beam lithography offers much better resolution. We're gonna talk about the image analysis using the focused ion beam today. And then since this ion beam can produce about 4 times higher backscattered electron signals, so that is why it is kind of pretty good when somebody needed to observe a sample using the backscattered electron. Focused ion beam can deposit films directly. So using this way, people make a device, and ion milling, instead of we are doing some pattern definition and then do a following etching, we can just directly etch, sputter away for some substrate. So that's the one of the options we can use out of the focused ion beam. So this is the typical configuration of the focused ion beam. So it normally has 2 columns. One is an electron column. So this column is almost the same as the scanning electron microscope. And then we have another column. That one is kind of similar in the arrangement of the columns like an SEM, but the source is an ion source. So we have a source for ion and then source for electron. And then here is the stages, and then this is the main chamber. So this is an actual tools, which is an this model of the focused ion beam. So it has a column for electron and column for ions, and then it has a platinum gas injection system. Using this way, we can deposit platinum. And then this is the stage motor, so we can just tilt the stages. And this is the another side. So the chamber door open like this way. And then in this case, in this side, we have another kind of a gas source which can deposit tungsten. And then there is another kind of a probe, which is just a needle made of metal. And we'll talk about where we use this Omni probe during the lecture today. So this is the inside of the chamber. So this is the lens for the electron beam, and this is the lens for the ion beam. and then this is the sample stages, and then this is the gas source for the platinum, and then there is a backscattered electron detectors, and then that's pretty much it. So these stages either positions at zero tilted, and in this case of that, this stage is kind of normal to the electron beam column. And when we rotate these stages to 52 degree, if then this stage is normal to ion beam source. So in the normal scanning electron microscope, we use an entire screen for a one image formation. Since for the focused ion beam, since we have two different kind of a source, so we can divide one screen to the 4 windows. So the image what you are seeing on the left top corner is an image from the electron beam. This is an image from ion beam. You can select this image for a backscattered electron detector. And then this one is a chamber scope. And then depends on the application, we can just use one of these 4 windows to the screen. So we can see much wider areas, and then we can work much easier with this kind of a big screen. So let's talk about how to operate focused ion beam. So as I just mentioned, there is one column for electron beam and another column for ion beam. But to use this kind of electron beam and ion beam together, those kind of a focal point should match. And then we call that focal point which has the same focus, we call that as a eucentric point. So this eucentric point is already fixed, but as you load your samples, depends on the height. If you make a focus using the electron beam, you can make the focus in every G positions. But if you just tilt these positions to 52 degree, if then these positions does not match with the focal position of the ion beam, so using the position of the stages, we should find out this eucentric point, and that's pretty important for the focused ion beam operation. So when we match the sample stages at the eucentric point, we can just work both using the ion beam and then electron beam. So for example, when we want to cut some specific area in your sample, when you matched your kind of a samples positions to the eucentric point, if then while you are observing that specific area, you can cut using the ion beam. If this eucentric point is not matched, if you are seeing some area you want to kind of a cutting, even though you are seeing right position using the electron beam, using the SEM mode, scanning electron microscope mode, those kind of a slicing, the ion sputtering area is kind of a totally different area. So that is why this point should be aligned before we start any kind of a work. So how we match how we find this kind of a eucentric point? So when you are focusing a sample, this is the image out of the electron beam, and this one is the image out of the ion beam. So since it is tilted to the 50-degree tilted, so it is normal to ion column. So it's kind of a top view. And then this one is a 52-degree tilted image. So you can see some of the side structures like this. So this is the one of the area we wanted to use, kind of ion sputtering, and then just to observe the cross section. So first we need to do the alignment. So first what we need to do is an focused one's targeting area using scanning ion electron column, and then just rotate it to the ion 52 degree, which is normal to the ion column. If this kind of your sample is not positions to the eucentric point, as you rotate your samples, these images just keep changing its location. It is kind of keep moving to one side to the other. And in this case of that, you roughly lower the G point of your stages, and then do the focusing again, and then tilt the stages again until you do not see those kind of movement of the images. We need to keep doing this kind of processes. So once we find some specific position of the stages, some specific G position, which does not move these images as we tilt from 0 to 52, we just checking with this kind of ion beam. But in most of the cases, there is some small mismatches between the center of your targeting images in the E-beam column, and then this one is an ion beam. So in this case of that, we can just simply move this targeting areas to the center. So using those kind of a fine alignment, we can just match the position of the samples just right for both the E-beam column and then ion beam column. So this is the kind of a final process to make the eucentric point. So it is something like this. So once we got this kind of a eucentric point, as we are observing some specific point, we can just do a slicing, and then those kind of slicing is always have this kind of angled. So as we just tilted, we can just easily see the cross section of a sample. And as I mentioned, we can also deposit some metals, which is platinum and tungsten. So the way of we are depositing this kind of metal is kind of very similar to the CVD. So using ion beam, we can locally heat it up a sample. So locally, this area is kind of, the temperature is kind of pretty high. And then as we just flow the reaction gas in this kind of a local area, because of those kind of a high temperature, we can deposit some film. And then as we just move the stages, we can just make some film like this. So using that way, we can easily form this kind of a metal layer on any kind of area on the substrate. So the deposition of this kind of a metal layer is kind of as easy as this. You first find those kind of a eucentric point, and then where you just input that the connections flowing source gas, and then this is the gas injector for the platinum. So as we just put it in, it just approaches to the very close to the sample stages. And then as we select, if we just want to deposit the metal about this kind of an area, as we are drawing some of the features using PowerPoint or those kind of a simple tool, we can just simply draw the area we want to deposit that metal. And then if we want to control the dimension more precisely, we can open a window, and then we can just adjust the dimension more precisely by typing the numbers into the table. So once we just do this, and then just press running, if then those kind of metal layers kind of deposited layer by layer, something like this. So we can just deposit whatever. This is a side view, so this is a substrate, and then this is a platinum, for example. So we can just deposit as thick as metals as we wanted. So, and during the deposition, we can check the progress using the SEM. But in this case of that, instead of we are just observing a live deposition process, we wanted to use a snapshot, because if we just keep turn on the detectors, those kind of deposition process can contaminate those kind of detectors. So we just wanted to take a very quick snapshot and then see the progress, and then using those kind of discontinued snapshots, we can just monitoring if those kind of deposition process is happening as we wanted. So this is the images of the deposited platinum, and then this is the tungsten filament hairpin used for the SEM electron emitter, but this one is a 52-degree tilted, and then this one is a 0-degree tilted from the ion beam column. So that is why it's kind of a little bit not straight, looks like a not straight for the 52-degree tilted image out of the electron beam images. So the ion milling is kind of a very important method. So if we want to see the cross section of your samples, we can, after we just deposit this metal layer, we can just decide how much we want to open through the sample, and then you can just simply draw the area you want to cut. So, and then just to change the ion energies, because depends on the ion energies, you can sputter out the substrate, or you can just minimize those kind of damage on the substrate, and then just observe the images out of those kind of ion beam process. So since we want to have a physical bombardment to remove these materials inside of this rectangle, we might want to use a pretty high current density. And then if we push run, if then, as you can see, it's just cutting that rectangle area, something like this. And then as you can see, those kind of a cut area is not clear, as you cannot see any details about those kind of a side view. That's because for this kind of initial cutting, you used pretty high energetic ions. So that is why when those kind of ions just to do the physical bombardment and then just to sputter out the ions on the substrate, it also laterally damage on this side. So that is why this area, what you are seeing right now in here, is kind of a little bit blurry because this side is kind of very roughly sputtered out. So we can change the ion beams to be much smaller in current. So using a much lower energy of the ion beam, we can just fine policing of those kind of a sidewall. So using that way, we can just see the area much cleaner. So something like this. So this one is kind of cleaner than this area. As you can see, there is this kind of rough images was removed. So for this kind of a cleaning cut, what you need to do is the same. You just decide how much you want to do the cleaning cut, and after we fix the area we want to cut, we just select the ion beam energy, ion beam current, and then just push the button, and then it can just make the cleaning. So these images, what you are seeing right now, is made out of secondary electron beam. It is on SEM images using the secondary electron detector. So that is why everywhere looks the same, and then you don't see any kind of compositional information from this observation. But as I mentioned in the previous slide, actually this ion beam can generate about 4 times more backscattered electron signal. So even with the same kind of material, depends on its angles, it can just show some kind of a contrast between the grains to grain. That is, on each of the grain has a different kind of direction of the single crystalline structure. So one structure, the alignment of the atoms is kind of much denser than the other, and then those kind of a different kind of a density can produce different kind of contrast. So with the same kind of area, when it was not tilted, it is just gray. When we tilted it to the 15 degree, the same area becomes black. And then as we tilted further to the 30 degree, the same area is contrast is kind of very bright. So even with the same area, with the same everything under the same conditions, depends on the angle of the sample, we can see different kind of contrast. And then this also gives different kind of compositional information, because those kind of backscattered electron signal getting higher as the atomic number is kind of getting bigger. So for this one is on tungsten filament. So all materials are made out of the tungsten. So in this case of that, the contrast to what you are seeing right now is based on the different kind of orientation of the grains. But this kind of a different kind of intensity of the backscattered electron also shows the different kind of a contrast between one element to the other. So we're going to talk about the focused ion beam application. So at the material synthesize sections, we talked about those kind of VLS technique. And as we already discussed, this kind of VLS technique using the catalyst metals and then some kind of source gases grow this kind of a bunch of not well aligned nano tube structure. So one of the way we can make this type of the device or characterize this kind of a nanotube is on just harvesting this randomly grown nanowire using the razor blade. So just scratch out this surface of the substrate and then just take all these kind of grown nanowires to a vial and then just mixed with a solution. So as we just spin coat this solution mixed with the nanotube, or just to apply on a substrate and then just wait for the dry. If this is the substrate, some area, those kind of nanowires are all kind of gathered together, and then there will be a area nanowires are pretty isolated. Since we are using the focused ion beam, which has two columns, one is an electron beam column, which can be used as an SEM. So using this kind of SEM mode, we can find this specific area, which is pretty isolated. So we already talked about how we can deposit metal layer. So if we find this kind of isolated area, we moved to there and then just simply draw this kind of a square, this kind of a rectangle, and then do the deposition. If then, we can just deposit this kind of a platinum or tungsten metal contacts on this nanotube grown by the VLS technology. So using this way, since we have 4 contacts, we can just measure the electrical conductivity of this kind of nanowire. And then if we want to make some kind of a device, we can just use one contact as a source and the other one as a drain. And then we might want to have some gate dielectric deposition before the gate electrode definition. Then we can make some kind of a transistor structure as well. So this is the kind of one way we can just use this kind of focused ion beam. Another thing is the TEM sample preparation is kind of a very powerful area. So as we discussed in the previous lecture, the TEM sample is we make the specific images as those kind of electrons just to transmit the samples and then just forming the images at the final imaging plane. So this electron beam should transmit the sample. So the thickness of the sample should be thinner than 100 nanometer. So when we have some samples, like we have a kind of let's say we have a device, we made the transistor structures on the 4-inch wafer. and then we want to observe those kind of a cross section of the transistor using the TEM. Most of the 4-inch wafer is kind of a wafer thickness is about 400 to 500 micrometer. So to make this kind of a TEM sample without using the focused ion beam, what we want to do is we want to cut the samples to the 4 pieces. So we will have a 4 rectangle after cutting. If then using the just an epoxy, we can just buy from a kind of a Walmart or that kind of places. We can first bond these two, this kind of active area facing each other, and then put another one on the back side over here, and then something like this, and then clamp this stack, and then just to bake it until this kind of epoxy just cured. And after that, what we need to do is just grinding, polishing these samples as thin as possible, something like this. So we put these sandwich-like structures to the some of the bigger structure. So we just grabbing these dummy structures, and then using those kind of sandpaper, we just polish this stack to these directions as thin as possible. So until when we get to the closer to the low of the micrometer, we cannot feel those kind of steps over here. So in the case of that, we just put this one and then transferred it to the drill, which has an 3 millimeter in diameter. So the reason why those kind of drill is on 3 millimeter in diameter is, as you may remember, we can use any size of the sample for the SEM, but the TEM, those kind of kappa grid size, its diameter is kind of fixed as a 3 millimeter. So that is why we just cut in the middle of the samples as a 3 millimeter, and then just to move this kind of a 3 millimeter disc of the samples to the kappa grid, and then just to using the epoxy, we just fix that samples on the kappa grid. So far we just go through about halfway of the sample preparation. So after this, what we're gonna do is there is another kind of a small wheels, kind of a turning like this, and then we positioned this kind of a sample loaded kappa grid, and then as these kind of wheels kind of keep rotating, it just making the center area thinner and thinner. So this kappa grid is kind of has on hole. So what happened is there is a light from the back side of this kind of a tool, and then it has some kind of a simple optical microscope. So as we just keep polishing the center of the sample, we sometimes just check the samples, just applying the light from the bottom. So as those kind of thickness of the silicon is getting thinner and thinner, and then at some point, those kind of color of the silicon, as we apply the light, becomes red, and that means those kind of thickness of the sample is kind of very thin. So after finishing this kind of a final mechanical polishing, we transfer these samples to the ion miller, which has a pretty small in chamber, and then it has we load the sample something like this, and then this kind of a special chamber has a very well aligned ion beams just focusing in the middle of this kind of a 3 millimeter in diameter of the samples. So using this kind of an additional ion beam millings, we can just make the center of this kind of a stack area much thinner than 100 nanometer. And then at some point, we just stop and then just load these samples to the TEM. And then if the thickness of the sample is kind of just right, if then we can just do the imaging process. But if those kind of sample is kind of still too thick, if then we should take these samples out from the TEM and then load it back to the ion miller, and then just to continue those kind of a thinning process. So as you may imagine that this whole process, making one sample, takes easily around 3 to 4 days. But even for that, if we have the transistor structures nowadays, is kind of entire structure is kind of smaller than 100 nanometer. So at some point, we cannot find those kind of samples. We spend that much of the time. Does not just cut the right place. If this is the kind of dome structures, if we wanted to cut the center of the dome, it could be cutting a little bit shifted or totally shifted. So if we are using focused ion beam, it's kind of very easy. First, we are using SEM mode. So using the scanning electron microscope mode, microscope, we can just finding the area we want to make the sample. So in that area, we deposit this protective film, which is the metal bar. And it takes less than about 10 minutes to deposit this kind of a metal bar. And then we select the area we want to cut. And then we can just cut the area something like this. So in the side view, this is the final structures we want to achieve. So this is the substrate, and this is the protective metal bar. So this is the goal side view we want to achieve. So after we slicing one side of the sample, we just draw another rectangles to slice the other side of the interesting area. So using that way, the side view of this sample is exactly something like this. So for this kind of a slicing, since we used very high energetic ion beam, what we wanted to do is we wanted to cleaning the surface of this area. So we will do those kind of surface cleaning. And then as we just thinning both sides, we draw these kind of structures. So instead of everywhere is kind of connected, we can just cut out this much of that kind of a thin piece of the samples. So at this point, you may remember when I just showed you the typical configuration of the focused ion beam. There is an kind of a metal bar called as an omniprobe, which looks like a needle. So this is that omni bar. So we just put this omni bar and then just to make this kind of omni bar positioned as close as possible to this kind of a thin piece. And then at the next step, we just deposit same metal we used for this kind of protective layer formation. So by the metal deposition, we can connect this thin piece of the samples with this omni bar. So here is a two option. One is on using the focused ion beam. You can just further sputtering and then just to make the this area to be disconnected, or this sample is kind of already thin enough. So if you just manipulate those kind of omni bar, you can just physically break this thin piece of the samples. And this thin piece of the sample already lost this kind of a foundation on the bottom and then the side. So you can easily break these samples out. And then using that way, we can achieve this kind of a thin piece of the sample, which is located where we are interested in the sample. So once we just take these samples out, we can load those kind of a 3 millimeter specific TEM copper grid to the system. And then we can just transfer these samples to the edge of this kind of copper grid. What you are seeing right now is the copper grid. This is the copper grid. And then those kind of a copper grid are designed for this focused ion beam process, even has an identification numbers or characters for each of the port. So if you slice multiple samples out, if then you can just write down, you just take one samples out from some areas and then just to mount the samples in the port A, and then the sample number B from the other areas, and then just to mount it on the port number B or something like that. So using that way, you can mount as many samples in very many different kind of interesting areas. And then you can just integrate all those kind of samples into one copper grid samples. And then as you just the way of mounting this sample is simply move these samples to that port and then just depositing metal layer between this port and then the samples. And after making these connections, you just draw another kind of a rectangle over here, and then using those kind of ion beam sputtering, you can just disconnect those kind of connections between the omniprobe and then the sample. So using that way, we can transfer the samples attached to the omniprobe to the specific port in the copper grid. So this is the final images of those kind of a sample. And this is the port. So using this way, we can easily prepare those kind of a cross-sectional view for the TEM samples. And then since we find out searching for that kind of a specific area using the SEM, so that is why this kind of a cutting area is kind of very precise. So it has a much more possibilities to be the area we wanted to go through. So So we talked about the application for the TEM sample, and then another application is using the metal deposition. We can make some kind of a device out of those kind of randomly distributed nanotube. Another one is we can use this focused ion beam as a lithography application. So the techniques we discussed at the E-beam lithography was on very similar techniques, like on substrate with spin coat resist, and then as we just write on the resist layer, we can just simply switch this electron beam to the ion beam. And then this exposed area depends on the type of the resist. We can remove the exposed area, or we can just remain in those kind of exposed area. One thing we can do only using ion beam is if we want to achieve this kind of a final structures on substrate. One thing is we can implant ions to this area. So this is the substrate. In this case of that, we don't have any resist coating. We just simply implant ions, something like this, on the substrate. So this area, these areas with those kind of ion implantation is kind of surface is kind of pretty different from this pure substrate. So if we are doing dry etching during the following process, those kind of a modified surface provide different kind of an etch rate. So we can achieve this kind of structures pretty easily. Much simpler way to achieve this structure using ion beam is, as I showed you many examples, we can just directly sputter out the ions from the substrate. Using that way, using the ion milling, we can just directly remove those kind of atoms on the substrate, and then we can just making these kind of structures directly. So focused ion beam, it offers kind of very many options. So this tool is kind of most kind of versatile options it can offer, especially for the nanotechnology. So it not only used for, as we just mentioned in the previous slide, it can be used for the lithography, and then the image analysis is another kind of a good area, and then the film depositions allows to making device directly, and then the ion milling can do the nanoscale dry etching directly. So using this kind of a way, it just offers kind of a very many options, especially in the focused in the nanotechnology device fabrication and analysis. So this is it for today's lecture, and then next lecture we're gonna talk about the scanning probe microscope. Okay, thank you.